Good afternoon, Manoj. We will start in 5 minutes if somebody joins. Okay. So you can also switch off your video. No need to keep it on if you want.
Okay.
I hope my screen is visible. So, good afternoon. I am Srijita. I am a PhD student of from IIT Guwahati. So today I am going to take the live sessions for the solid fluid operation. Then let's start. So first question is a basic one, that what is a solid fluid operation? So can you tell me what?
Okay, ma'am, good evening. I am Manoj Kumar Gandwale.
Yes, tell me the answer.
Ma'am, my first doubt question is
Hmm.
assignment.
Hmm. Tell me the assignment.
Ma'am, in particle analysis, the following result: this mass particle in gram 25741 and the mean size of particles micrometers
Hmm.
350, 240, 200, 150 and 100. है ना? So
Hmm.
then,
Which
ma'am,
question number? Can you see my
question
screen?
number two, assignment. Ninth, ma'am.
Ninth. Yes. What is the question?
Uh,
What is your question?
to calculate the volume surface bin diameter of the particle in micrometer.
Hmm.
तो मैम एक्चुअली यहाँ पे मैम मास पार्टिकल दिया
Yes.
है ना, एंड
Yes.
द मीन साइज पार्टिकल्स भी शो है
हाँ.
ना. तो हाँ, तो द वॉल्यूम सरफेस डायमीटर कैलकुलेट करना है. तो मैम एक जो आ रहा है मैं कैलकुलेट कर रहा हूँ, तो वो यहाँ पे जो ऑप्शन हो रहे हैं 193 196 दिस, बट मेरा जो आ रहा है आंसर
Hmm.
पॉइंट में आ रहा है. तो प्लीज टेल मी.
Just a minute. Hmm. So it is the summation of 1 minute.
मास फ्रैक्शन
Hmm.
is formula calculate the volume surface.
Yes, so it is the formula is summation of 1 by
एक जी
no
जी
summation
1
is
बाई समय.
1 by summation of xi by di,
जी
right?
जी.
Yeah.
यस.
So you are doing this, still it is not getting the answer.
यस. में समेसन ये 1 है, तो समेसन मास फ्रैक्शन तो डिफरेंट दिए हुए हैं ना मैम. तो सम आप समेसन आप एक्स आई हो जाएगा एंड दिस
So
2 प्लस
it will be
5.
2 by divided of 2. So I can show you that. Let me show this screen. So if it is so if it is the mass at here it is 2, then 5,
यस
7, 4,
यस
1. So you have to sum it up all. So it is the individual mass of the particles are given.
यस
So
यस
for x1 it will be 2 by what is the summation of 2 plus 5.
यस
2 plus 5. um,
प्लस
plus 7.
Yes.
Just a minute.
And this sum of total 19.
Yes, 2 plus 5 plus 7 plus 4 plus 1 equals to 2 plus 7, 14, 18, 19. Yes. So 2 by 19, this will be the x1. x2 will be 5 by 19. This is how we have done. 7 by 19, x4 will be 4 by 19 and x5 will be 1 by 19. So now if you go back to the question, these are the mass fractions of the particles and this is their particle size. So now if you do this, you can get, I think. You have done this way? Have you done this way?
Yes, ma'am.
Still you are not getting. Okay. Mm. So let me calculate.
Ma'am, this mass fraction is different. So overall mass fraction divided by every particles of mass fraction.
Yes.
And
Yes.
this
Yes.
total calculate and this divided by summation of xi divided
Hmm.
by dpi after calculate.
No, individually you have to calculate. Like first x1 is what? X1 is, we have got x1 is 2 by 19. So we will
Yes.
do that. So final it will be in the form like this is 1 divided by 2 by 19 divided by the value of the particle, mean size of the particle. That is 3. For the first case, it is 350. So it will be 2 by 19 into 350. For the second case, it will be 5 by 19 into, what was the value? 240. So it will be 240.
Yes.
Then 7 by 19 into, the particle size is 200.
200.
It's 200.
Plus,
Then
plus
4 by 19 into
290.
150. Then
Yes.
again, it will be continued 1 by 19 into 100.
Yes. Yes.
So you have to sum it up all the denominator and then you have to do it 1 by that whole number. Right?
Okay, ma'am.
So yeah, so you can do it right now also with me. Suppose the first one it is coming, so I am writing it again. So the first it is 1 by, the first one is coming. This coming 0.00030075. Okay.
Then
So
calculate this 1 by 36.
what? You calculate with me. See whether we are getting it or not. Is plus 0.00109996.
Yes. 1.5.
Then 19 into 200, 7 by it is 0.001842. The fourth term is 19 into 150 and it will be divided by 4. It is 0.001403. Finally, 90 into 100, 1 by answer. This is 0.000526. So now we have to sum it up all and then divide it. So it will be coming 0.00030075 plus 0.0096 plus 0.001842 plus 0.001403 plus 0.000526 and it is coming 1 by is coming 1 by 0.005168. It will be equals to 193, 193.5 micrometer. This is the answer. No, you are doing something, maybe some mistake. So the answer is
190.
A, 193.5. Yes.
Okay, thank you, ma'am.
Okay. So you understood your mistake, where you are doing mistake?
Yes, yes, ma'am.
Yeah. Okay. Okay. Fine. Any other question?
And question number 6, sorry.
Yes.
What is the viscosity of the slurry in Pascal?
Hmm.
Second, of volume fraction 0.435 of sphericity epsilon s is greater than 0.1. The viscosity of the liquid with which the slurry is made at 20 degrees Celsius is 0.0023 Pascal. Second, in the case of higher concentration, epsilon s is greater than 0.1 and low shear stress is less than 1 kilopascal. You can the Thomas 1965 questions this.
So what is the problem here? So the equation is given on already, na? So you have to just put the
Yes.
values there. You have to just put the values there, nothing else.
And this ma'am e to the power 1 epsilon.
Yes, e to the power 1.6 epsilon s.
Okay, okay.
The equation is given in the slide, na? From where Sarah was teaching, the equation is given there also.
Okay, ma'am.
So you can check there also. Yeah, it is 1.6 into 10 e to the power 1.6 epsilon s.
And calculate the answer is 0.00918.
Yeah, maybe. If it is coming exactly, that is fine.
Okay. Thank you.
Okay, okay. Any other question?
And next question, ma'am, 6. This question is on almost the formula based.
Question number 5.
6.
6 is this is the formula is also given. No?
Okay, okay, okay. Thank you. And the ma'am, question number 7. The opening size of the 20 mesh dollar standard series of the screen is.
Yes, this is also the zeta potential explanation in the given. It is the mu electrophoretic mobility is the option B. The velocity of the particles divided by V REL. And you can check go through the slides also, because all these are there only. I am not saying anything new.
Okay.
Hmm.
Okay, thank you, ma'am.
Yeah, thank you. So I will be doing some extra questions also. So let me start with that. So first one is a basic one. What is solid fluid operation? So can you tell me what is solid fluid operation? Because you are doing this course, so you must know this because this is the first line of the slide. Can you tell me what is the definition?
Yes, ma'am.
What is the question you are? Can you see the slide, right?
Yes.
Yeah. So answer this question. What is the solid fluid operation? What we are going to learn from this course?
The generally solid fluid operations is basically uh, different types of process, है ना?
Hmm.
Sizing of the solids, transportations, chemical synthesis, process, drying, mineral process, beneficiations, recovery of the volume of the solids, है ना?
Hmm.
Mixing, screening.
Yes. So it is the sum of the different type of process from where we are reducing the size of the solid particles, and also we are separating them from in different sizes, and it will be it has immense applications in our chemical industry. So that is why
Yes.
solid fluid operation is the basic subject.
This
Next,
process is mechanical, electrochemicals, chemical
yes,
process, then
chemical processes.
different.
Yeah.
Okay.
Hmm. So okay, so this is the very basic question. Next question, name of some of the mechanical processes in solid fluid operations.
Mechanical operations is the transport of slurry, solid transport, crushing, grinding, mixing,
Yes,
fluidizations,
yes,
condensations, है ना? Filtrations,
yes,
and
yes,
this
yes.
process are mainly mechanical operation process.
Hmm. Okay. So these are the mechanical process. Next comes magnetic separation is a chemical process. Is it true or false?
Mag- Magnetic separations.
Yes,
Mm, true, false, sorry, ma'am. False.
yes, it is false because magnetic separation is a electrochemical process.
Electro.
Next is the trickle bed reactor is considered under which of the following processes? Trickle bed reactor,
Chemical.
yes, it is chemical process. Next question is the process which is called what? Where new surfaces are generated by producing micro and nano size particles. Following which of the process is called where new surfaces are generated by producing micro and nano and size particles, nano size particles. So in which of the following methods we do that? Is it attrition, or is it grinding, or is it crushing?
This process is, ma'am, attrition.
Are you sure? This is the grinding process. You check with
Grinding.
the slides. Okay. So this is the
Okay.
grinding process. So in grinding, we grind the bigger particles, and it is creating some new size of smaller particles. That is why it is creating new surfaces, which is generating new surfaces. Next question is the separation of solid particles from solid fluid mixture is called the screening process. Is it true or false?
True.
I have said solid fluid mixture. So when we are separating solid from solid fluid mixture, it is filtration.
Yes, ma'am.
And when we are separating the size-wise solid particles, okay, size-wise distribution of solid particles is the screening. So these are kind of mesh, different size of mesh we have that you have seen maybe. So this is the different different diameters of screen, and we are separating different size of particles. So from solid particles, we are separating other size of solid particles is called the string, not the solid fluid mixture.
Okay.
Next question is the what are the different types of filtration process? What are the different types of filtration process?
Okay, just a minute. Light is.
So there are almost 4 type of filters used in the industry. So first one is the cross flow
Cross
filter,
flow.
then
Okay.
cake filter, then syringe
Yeah.
or capsule filter, and fourth one is the membrane. So if you go through the slides, you can see what are the cross flow filters. It is the filter designed to concentrate suspension of fine particles or colloidal material, and its size particles of size range 0.1 to 5 micrometer are generally separated. In the cake filter, cake which is formed, this cake filter is formed by the accumulation of the solid. Okay.
Okay.
In the syringe capsule filter, the filter is designed with a lock at inlet and fitting on the outlet of a syringe. And the membrane, you know, the different type of membrane we use, the cellulose membrane, nylon membrane for separation of different size of particles.
Okay.
Next question, what does it mean by PM 3.5? What does it mean by PM 3.5?
No, ma'am. Please explain.
So PM means particulate
Particulate matter.
matter. Yes.
Yes.
So when PM 3.5 it is written, it means in the particulate matter, in this type of particulate matter, the size of
Three.
particle diameter is
3.5
3.5, yes, or it's less, 3.5 micrometer or less.
micrometer.
Yes,
Okay.
3.5 micrometer is the predefined size. So it is well established form of expressing particulate matter.
Okay.
Next question. Particulate matter can be separated by cyclones. Is it true or false?
True.
Yeah, it is true. So
S
particulate
particle.
matter.
Yes, ma'am. Cyclone separator is the separate in S particles. So S particle is the particular matter.
Yes. Cyclone separator, the scrubber, candle filter, any kind of
Yes.
sedimentation can also separate particulate matter. Next,
Okay.
in which process gas bubble gets adhered to solid particles and separates them. In which process?
Process gas.
So here what happens? Some gas bubbles and creates adhesion with the solid particles, and they just become buoyant and separates the solid particles from the other fine particles. So what process is called this?
Fluidization process.
No, fluidization. In fluidization, we have to pass through the gas also. Not gas bubbles are generating because of the mixing, but we are sending gas. But it is the flotation. It is the flotation. Okay, so the particles which are maybe suspended, they will float out of the system because of the adhesion with the gas bubbles. This
Okay.
is the flotation process. Next, evaporator is used to remove the water from solid. Is it true or false? Evaporator is used to remove the water
False.
from
False.
solid. Yes, it is false because when it is takes out water from solution, so evaporator takes out water from solution, and dryer or drying process takes out water from solid.
Sure.
So here it is false. Next, what are the different types of dryers used?
Tray dryer, rotary dryer, drum dryer.
Yes, it is tray dryer, rotary dryer, drum dryer, continuous rotary dryer. Okay.
Okay.
Next, which process is driven by a mass transfer of a solute from a liquid solution to a crystalline phase? Which process is driven by a mass transfer of a solute from a liquid solution to a crystalline phase? So from the explanation itself, it is clear that it is happening, the solute,
Crystallization.
yes, the solute gets transferred from liquid solution to a crystalline phase due to mass transfer. So this is the crystallization process.
Okay.
Next, which process is used for separating and purifying chemicals? Which process is used for separating or purifying chemicals?
Thickening process.
No. No. Thickening process separates the suspended particles at the bottom. So it is the fractional crystallization.
Okay.
The right answer is the fractional crystallization. Next, what is the method of separation of solutes in leaching process? Like in leaching process, the separation of solute from a solid, solutes are separated by an insoluble solvent, right? So how
Yes,
this
sir.
works? So it is the adsorption capability of the solutes to the solvent. Okay. So due to the adsorption, the solutes gets captured to the solvent, and that is how it is separated. This is called leaching. Next question: in which process gases, organic mixtures are separated at a fixed temperature? In which process gases, organic mixtures and are separated at a fixed temperature? What is the name of the process?
Distillation process.
No, it is the
No.
gas. So at peak
Yes.
calcination. So what happens in calcination process at a fixed temperature, the
Yes.
solid particles converted into oxide, and in absence of air, the whole process is happen. So that is called the calcination process. So in this way, the different type of gases like CO2, SO2, NO2, organic impurities, and moistures are separated from the source. Next, the process of converting ore into an oxide in presence of excess air is called what?
Calcination.
No, in calcination, absence of air, and it is
Absence of.
said that it is presence of excess hot air. So both are different. Both of them are making converting ore into oxide, but one is presence of air and another is absence of air. So the answer is roasting. So roasting is presence of excess air, presence of excess hot air. And calcination happens absence of air. Next, talk about the different types of electrochemical processes. So I'm going to show you some videos. You may know this, but still. So different type of electrochemical processes are electrostatic separation, magnetic separation, electrodialysis, electroosmosis, power evaporation,
Ion exchange.
gas ion exchange, electrophoresis, and gas permeation. So each of the processes I will show through this video.
Chemical.
So you yourself can also search it, but
Chocoball. Chocoball.
so are you able to hear the sound?
Yes.
Yeah, so you can see here that this is the material feed, mixture of the particles are coming, and here the mixture of the particles are coming, and some of them are electrically charged, and in this conductor, the first one, this is the charged materials are stored, and all the non-charged material are stored in this uh, red portion. So this is how this is a charged material, and here the voltage are given. You can see here the voltage is given. Due to that, the green particles are separated from the red particles. This is the basic principle of electrostatic separator. Okay. Then is
Okay.
the
Can please share this websites?
okay. I'll share. I will share the slide only, so you can get the link from there.
Okay.
Hmm. So you can see here that. So this is the slurry feed. That means the mixture of particles are coming, and here in this middle region, some magnets are there, due to which these black particles are magnetic particles. Okay, so due to the presence of magnet, only the magnetic particles are separated from the right side, and all other particles are separated in the left continent. Okay, so these are the magnets, and applying these magnets, we are creating magnetic force, and that is how the magnetic particles are separated from the rest of the particles. Next one. Next one is the electrodialysis.
Electrodialysis.
So here you can see there is electric solution where positive and negative charge are there, and now they have attached the cathode and anode, and charge is supplied. And you can see that in the positive portion, that is the anode, where anions are present. Anions are coming, and in the cathode, positive ions are going. That is why they are separating the negative charge from the positive charge.
Okay.
So now they are creating multiple this type of separation. You can see that these anion selective membranes do not let pass the positively charged ions, and similarly the cation selective membranes do not let pass the negatively charged ion, and that is how they are separated in the plate. That means at the side they are separated, the positive and the negative. Okay. Yes, this is the simple electrodialysis. Now comes the
If you feel that using ChatGPT for your essays is cheating, but you still want some help with your essays, let me show you Jenny.
Electroosmosis. The charged colloidal particles move
This
under
is
the influence
electroosmosis.
of electric field during electrophoresis. If electrolyted by using porous Y and Z in compartment, the colloidal solution is placed in compartment X. The compartments Y and Z are filled with the dispersion medium. X is separated from Y and Z by using porous partitions P and P'. The levels of the
What is the
dispersion medium
difference between electroosmosis and RO reverse osmosis are same or different?
No, reverse electroosmosis happens in presence of electric field. So with the help of electric field, we are doing the separation. But in case of reverse osmosis, there is a concentration difference. So here we are not exploring the concentration difference. Here we are exploring the electric field charge is playing here, and in that case, concentration is playing.
in the capillary tube T and T' are noted. When a potential is applied at the electrodes, there will be flow of dispersion medium from one side to the other. This can be observed by looking at the levels of dispersion medium in the capillary tubes T and T'. The level of dispersion medium is observed to fall on one side and rise on the other side. If colloidal particles carry negative charge, the diffused layer has a resultant positive charge. Therefore, the dispersion medium will move towards negative electrode, and if the particles are positively charged, the dispersion medium will move towards positive electrode, since it has no resultant negative charge. In this method,
So here it is saying that this is the mixture, solution mixture, and here they are giving the positive electrode, and this is the negative electrode, and because of the voltage difference or potential difference, the positively charged particles are going in the opposite direction, and that is how they are separated. So this is mean the electrode, like electric potential, that is the voltage, is playing here. Not in case of normal osmosis, we separate with respect to the concentration gradient. Okay.
Okay.
So this one is the electrophoresis. It is also the presence of electric field which helps in separation of particles. And electrophoresis is applied in case of any biological material like protein.
Electrophoresis word break into electro means electricity and phoresis means movement. So what is electrophoresis? A technique used to separate charged molecule based on their size and electric charge in an electrolytic cell is called electrophoresis, or simply the migration of charged ions in a liquid medium under an electric field. It is used to determination of molecular weight of proteins and DNA sequencing. The principle of electrophoresis is based on the fact that charged particles, such as DNA, RNA, and proteins, can be influenced by an electric field. When an electric current is applied to a medium containing these charged particles, they migrate towards the electrode of the opposite charge. Procedure 1. Preparation. The gel.
So the biological matters like DNA, protein, even cancer cells also nowadays are separated with this electrophoresis or dielectrophoresis. So depending on the, if cancer cells are negatively charged or DNA, RNA are negatively charged, then it will go opposite to the positive electrode, and that is how it is separated from the normal cells or normal biological proteins.
Okay.
So this one is electrophoresis.
Separation in ion
This is the
exchange
ion
chromatography depends upon the reversible adsorption of charged solute molecules to immobilized groups of opposite charge. Most ion exchange experiments are performed in 4 main stages: equilibration, sample application and wash, elution, and regeneration. The first step is the equilibration of the stationary phase to the desired start conditions. When equilibrium is reached, all stationary phase charged groups are associated with exchangeable counterions, such as chloride or sodium. The second step is sample application and wash. The goal in this step is to bind the target molecules and wash out all unbound material. The sample buffer should have the same pH and ionic strength as the starting buffer in order to bind all appropriately charged proteins. In the third step, elution, biomolecules are released from the ion exchanger by a change in the buffer composition. A common way is to increase the ionic strength with sodium chloride or another simple salt in order to desorb the bound proteins. Proteins are desorbed relative to the number of charged groups on their surface. The final step, regeneration, removes all molecules still bound. This ensures that the full capacity of the stationary phase is available for the next run.
So this is ion exchange also depends of the cation anion, but here no electric fields are applied externally. So it is the separation of cations from anions depending on the movement, but no electric field is applied. This is the par vaporation. So par vaporation is the separation method depending on the partial vaporization through a polymeric or ceramic membrane. So if suppose a mixture has different kind of materials and the materials have different partial vaporization temperature. So due to that temperature difference, we can separate the some materials from the whole mixture. So this is the par vaporation. Last one is the gas permeation.
Hi, what's a membrane? A membrane is a selective barrier. It allows something to pass
pervaporation method and gas permeation, this is the membrane process.
Yes, this is the membrane process. So different kind of membrane are used for par vaporation and gas permeation, but both of them are membrane process.
Okay.
broke, but stop others. Such things may be molecules, ions, or other small particles. The membranes can be classified according to
So gas permeation is simple. So suppose a membrane is there and it has different pore size, and because of that, some molecules are going through the membrane and some are retented. So that is how
the type of
membrane works.
material or depending on the pore size. Today we are going to talk about lipid membrane. Itself, it has amazing structure and signal abilities, but to stick to very basic, it is made of a phospholipid layers. The head is polar and the tail part is no polar. Some molecules have no problem going through the cell membrane, and they'll go through the phospholipid layer. Very small no-polar molecules fit in this category and are agreed, like some gases, oxygen and carbon dioxide for example. This is known as simple diffusion. Also, it doesn't take any energy to form these molecules in or out, so this is known as passive transport. Simple diffusion moves with the flow, meaning it moves with the concentration gradient. Molecules move from a high concentration to a low concentration. So when you hear someone saying it's going with the concentration gradient, then that's what that means. They're going from high concentration molecules to low concentration molecules.
Okay, remember when we say that the membrane has amazing structure, it's because we haven't mentioned about proteins in the membrane, and some of them are transport proteins. These transport proteins have light channels, some of these change the shape to get items across, and some of them open and close based on a stimulus of some kind. It helps with molecules that may be switched across the membrane or their own. This is known as facilitated diffusion. This is still diffusion, and it still moves with the concentration gradient of high to low. It doesn't require energy, so it is a type of passive transport. It's just that the proteins are facilitating or helping things pass. Target ions often require a protein channel to pass through. Glucose needs the help of a transport protein to pass through. In osmosis, for water to travel at a fast rate across the membrane, it passes through protein channels called couponins. These are all examples of facilitated diffusion, which is a type of passive transport.
But what's happening to triphosphate and sodium potassium?
It is in general explaining how the membrane works. So that is how for gas membrane also this is the same.
Okay.
Next, what is the example of gas phase non-catalytic reactions? What is the example of gas phase non-catalytic reactions? So the example is natural gas combustion. Natural gas means suppose methane, and it is combusted in oxygen, and it will produce carbon dioxide, water, and other materials. So that is not important. The example is natural gas combustion. Next, biochemical process is an example of gas solid liquid phase reaction. Is it true or false? Biochemical process is an example of gas solid liquid phase reaction. Is it true or false?
True.
Yes, it is true. So other gas solid liquid problems are fluid bed catalyting, cracking, hydrotreating, and cultivation of microorganisms and biochemical process, obviously there. And next, what are the different types of particle shapes and their definitions? So you know that properties of particle is very important in separation or size reduction. In case of solid fluid operation, so this
Vesicular, angular.
yes. So properties of particles, one of them, the shape of particle comes under property of particle, along with there is size, strength, porosity, particle outline, zeta potential are also important properties for particles. So for the shape, there are different type of shapes. So first one is the circular,
Vesicular,
then angular,
angular,
then fibrous, hmm,
fibrous,
then granular,
granular,
then spherical or cuboid or any type of defined shape. So in the acicular shape comes needle shaped or rigid, like long particles. This type of particles will come needle shape.
vesicular.
This is acicular. So short question can come from this, that what type of shape is comes under acicular shape. So you can remember this. Next is the angular. Suppose some particle have hard angles. So these are the type of angular. Fibrous one is the thread-like, you know that this thread-like structure. That is the fibrous. Granular is irregular shape particle. Any type of shape particle, and spherical is regular shape particle. That is spherical, then there comes the cuboid and cone shape particle, all in. Next, what is the aspect ratio of a rod? What is the aspect ratio of a rod? What is the aspect ratio of a rod? So the definition of aspect ratio is
This aspect ratio range
diameter per
0 to
length.
1. But
Yes, diameter per length. So for the case of a long rod, what will happen? Its diameter is very small. So D is very small to the length, that is L. So we will take it almost 0. So in case of rod, it is almost 0. Okay. Generally, aspect ratio comes under 0 to 1. Generally, the aspect ratio of any particle comes under 0 to 1. Next, what is the sphericity? What is sphericity? So, you know, I think, but still I am explaining. It is the surface area of a sphere. Surface area of a sphere having same volume of particle divided by
surface of the particle.
surface area of particle.
Right.
Here particle means any shape of particle we are considering. So in the case of irregular shape particle, we don't know what is the diameter, what is the length. So for those type of particles, we calculate sphericity. So the expression of sphericity is pi s equals to 6 by dp by sp by vp. You know how is it coming? You can do the derivation, right? If not, should I do?
6 by dp.
6 vp, same. 6 vp
Yes,
by
yes, yes.
dps. You know how is it
Okay.
coming?
एंड जिस फार्मूला में मैं पाई बाई 1/3 6 bp by 2/3 divided by ap.
Yes, so how is it coming? So let me show you. So what does it say? That it has same volume. The particle has same volume with the sphere. So we know the surface area of a sphere, right? So what is the surface area of a sphere? So surface area, suppose it is AP. Surface area of a sphere is 4 pi r square, if r is the radius of the sphere. Okay, so if this is, suppose this is the radius of the sphere, so this is the surface area, and if we want to explain it in terms of diameter, so what will be 4 pi dp by 2 whole square, right? So it will be pi dp square. dp is the diameter of the particle, not particle, the diameter of the sphere. In case of now, so now the sphere volume is Vp. So how is it calculated? 4/3 pi r cube. This is the well-defined formula. So now we will change 4/3 pi dp by 3 whole cube, that is 1/6 pi dp cube, right? So yes, this is the, so now what is happened? So now we can write from here only, you can write, see, Vp into 6, it will be pi dp cube, right?
Okay.
Right? If we multiply, if we bring the 6 here, it will be 6 Vp equals to pi dp cube. Then it will be 6 Vp by dp. It is pi dp square, right?
Okay.
And pi dp square is nothing but the surface area of the sphere, right?
Yes.
So now if we go back to the formula, what is there? Phi s is the surface area of the sphere divided by surface area of the particle. So surface area of the, so phi s will be surface area of the sphere, that is AP, and surface area of the particle, that is, suppose SP is the surface area of the irregular shaped particle. Okay, so now we know the AP's expression is this 6 Vp by dp into sp. Okay, so this is how the formula comes. This is very important one to remember. You can directly apply it in this form also, phi s, or otherwise you can remember the procedure also. You can compare with the volume and then also come to the result in your problem. So if you don't remember this expression, that is not also a problem. Okay. Okay, so can you do one problem on this? Okay, you do a problem on this. I think it is also given in your almost also given in the assignment, but still you do. So suppose so the question is find the sphericity.
Yes.
Find the sphericity of cylinder particle of diameter 3 millimeter and height also 3 millimeter. So there is a part different this is a silicon cylindrical particle which has diameter 3 millimeter and height is also 3 millimeter. So now calculate its sphericity. Calculate and tell me. Height and diameter both are 3 millimeter. So are you able to do? First, compare with the volume. So from the definition itself, you know that cylinder and the irregular shape particle and the sphere, both of them have the same volume. So what will happen if in this case, what will be happen? The first is volume of sphere and cylinder will be same, right? As per the definition, it is given.
G.
Yes. So now, what is volume of sphere? That is 4/3 pi r s cube. Rs is the volume. Suppose radius of the sphere. Yeah. And what is this? Is the sphere. Suppose it is rs, and this is it. It is 3 is the diameter. So we'll be calculating the radius. So now the cylindrical for the cylinder the diameter is suppose only r. So what will be the expression of volume of a cylinder? That is pi r square h. So r is the given already. R is given, right? 3/2. That will be r for cylinder and h is just simple 3. Okay. So this pi will be cancelled out. So what will be rs cube will be 3/4 r square h, right?
Yes.
So now 3/4, what is r? R is 3 millimeter, right? So r is not 3 millimeter, d is 3 millimeter. So r will be 3/2, that is 1.5 millimeter. Okay. So 1.5 is square into the height is 3 given. So how much is it coming? So it is coming So it is coming 5.0625. This is rs cube. So what will be rs? Rs is the one point 717 millimeter. This is the radius of the sphere. Okay.
Yes.
Now,
Yes.
yeah.
What is calculate of RSQ 5.0625 and then after result RS equal to 1.717.
So it
This
is, we
is
are calculating RS cube, right? So we are doing cube root of 5.0625. Got it?
okay.
Yeah. So this is the RS cube is 5.0625. So we are doing cube root of RS, cube root of 5.0625. So then it will give the radius value of the sphere.
Scientific calculator are
Yes, scientific calculator is there.
okay. Thank you.
Hmm. So next what will happen? Now we know the radius of the sphere also. So now as per the definition, what is the surface area of sphere? Surface area of sphere and surface area of particle.
Particles.
So surface area of sphere is 4 pi rs square and divided surface area of here our particle is cylinder. So it will be 2 pi r into r plus h. Okay. So now we know all the values of both particles R we know. So we did the comparison of volume calculation because it is given in the definition of sphericity that the volume of the sphere and the cylinder will be same always while calculating the sphericity. So with the help of this calculation, we calculated the value of radius of the sphere. We didn't know that. But now after the calculation we know, and now we can easily calculate the sphericity, the surface area and as well as the sphericity. So just put the values 4 pi r square we just calculated 1.717 whole square and 2 pi, this is already given, r is 1.5 given, so 1.5 plus 3. 3 is the height of the cylinder. Yes. So what is coming? So the upper one is coming 37.28 divided by 2 pi so it is 42.39. So if you divide this, what will happen? It is coming as 0.873. So the answer of this cylindrical particle sphericity is 0.873. Okay.
Okay.
You got the. There is a problem in the assignment also. I hope now you will be able to solve this if you have not done already. So you understood, right, how this is calculated?
Okay.
Yeah. So proceeding to the next question. Sphericity of a particle gives the information about particle roughness. Is it true or false?
This is true.
No, particle roughness means how rough it is. So like if it is rough, so that information cannot give, sphericity cannot give. It will be given by particle outline. So there is a term called particle outline. Yes. So particle outline will give the information about the particle roughness. So it is false. Next, what is the size range of fumed silica and granular fertilizers? If you see, there is a long list of different type of size of particles. So from there, so fumed silica is in the
10 to
range
the
of,
power minus 2 to
yes,
10 to the power minus 1 micrometer. micrometer.
Yes, this is the range of fumed silica. And for granular fertilizer, the range is 10 cube to 10 to the power 4 micrometer. So this one is the bigger one. Next, what is Gelder's powder classification? What is Gelder powder classification?
At this gel dulled powder classification at the ambient conditions, catalytic reactions, combustion, gasification, drying.
Yeah.
Deproduction.
So this is the different type of set of particles are there. So first one is the group A, right?
Yes.
So group A this is the when fluidized by air at ambient temperature give a
General powder classification is the 4 group A, B, C, D.
yes. So I am explaining one by one. So group A, when you can write also this, when fluidized by air at ambient temperature give a region of
Region.
non-bubbling fluidization. So initially when group A type of size of particle, group A type of particles are there, when it is fluidized by air, it does not create bubbles inside the fluidization bed initially. But if the velocity increases, if velocity increases, it will give bubbling fluidization. Okay.
Okay.
This is the first type of particle, that is group A. Next one is the group B. So group B type of particles gives only bubbling fluidization. Okay, under ambient conditions. Then
This 4
come,
group are must ambient condition.
yes. So group A initially does not give any bubbles, but when we increase the velocity, it gives bubbles. But group B from starting only gives the bubbles. Group C is a very fine powders, the smallest size of particles in the group. So these are very fine powders. They are always cohesive because the particles they are very fine, right? So their size is very small. So the molecular interaction between the particles are very high. So that is why the particles cannot separate with each other. You can see that we use the talcum powder. It is always formed like a lump. We cannot separate each of the powder particles, right? So that type of particles are group C particles. Okay. And last one is the group D particles. This is the large particles in the section. And they are distinguished. They are distinguished by their ability to produce deep sprouted beds. That means when we flow the air through the fluidized bed where group D large particles are there, it will create a sprouting kind of thing. So I will show the videos of each particles one by one. So first is the group A particle. Okay. So the left side video is for the non-bubbling expansion. That means the gas flow rate here is low and it is not creating any bubbles. So it is creating kind of homogeneous mixture. Okay. This is creating a homogeneous mixture at the low air flow rate. But when we are increasing the air flow rate, it will create the bubbling fluidized bed. That means from bottom to top, bubbles are generated. See, initially at the initially at the bottom stage, small bubbles are generated. Then these small bubbles are coalesced with each other. That will create bigger bubbles. And again, when it is reaching at the top of the fluidized bed, it will creating bigger bubbles, and they are opened through the top portion. Okay. So this is the bubbling fluidized bed of group A powder at higher velocity.
Okay.
Next comes the group B particles. So group B particles from the initial stage only they are creating bubbles. So you can see here that initially from lower velocity, lower flow rate of gas also they are creating bubble. The particle size is little bit bigger than compared to the group A particle. Okay, so this is the group B particle. Next comes the group C particle. So just I have told you that it is kind of the talcum powder. So when it goes up, you can see when it is going up through a bulk of powder is going at the same time. Okay, and after some time it falls down, and between the particles at portion this air tries to make its way, and it is creating this kind of motion in the particles. So this is the smallest one. The fine particles are called the group C particles. Okay, so next is the group D particles. So it has the larger particles, and you can see that from one, yes,
solid form.
yes, you can see that here from one side only the air can pass through the bed, and it is creating some kind of sprouting kind of things at the top. Right. So
this is a fourth group of
yes, these are the four groups of gel dust particles.
Yes. Please, ma'am, 4:30 is the meeting, and so please, one question is explain zeta potential.
Yeah. The zeta potential I will explain. Okay. Okay, let me explain that. Achha, zeta potential is the next question. Okay, there is another question also. Let me just show you. You know, I think this is the Richards and Brown.
Other just next lecture is the continue, but today is the meeting 4:30. So
Okay, zeta potential I will explain. So
okay.
So today you want to listen or next day?
Yes, ma'am.
Zeta potential I will explain now.
Yes.
Okay, also I will upload this video so you can learn from there also. So right now I am explaining. See, this is a video you can see later. So the thing is, there is a electrode of opposite charge material. Okay, this is the minus negatively charged material is there, and there is a solution. These are the solution electrolyte. Okay, so this is light electrolyte, like our salt. Okay, so salt is Na plus Cl minus, right? So it has
Yes.
plus cation also and anion also. So what will happen if this is minus, that is negatively charged particle or electrode, whatever it is? So this, all the positively charged ion will stick to it. Okay, right? You know that opposite charge attracts. So if there is a negatively charged particle from start, so this for the salt, from the salt, only the positive charge particles, that are the cations, will go and stick here. Okay, and it will form layer. So in the first layer is this layer is fixed. That means whenever this electrode will move, this particle, this positive charge particle along with this electrode will move. Okay, so that is why this layer is called Stern layer. Okay, that is called Stern layer. Now in the second layer, all the charge are not positive. So this is positive, this is positive. Suppose there is negative charge 1. Okay, this is positive again. So that means in the first layer, when this is very close to the negative charge layer, only the positive charge is there. But when we are going little bit separate, little bit away from the negatively charged particle layer, here in the third layer there is a mixture of positively charged ion and negatively charged ion. Okay, so this will also create a layer, and that is called shear plane.
Yes.
Shear plane, yes.
Okay.
And after this also there are layer of charged particles. So plus, maybe minus is coming in larger way now. This is minus, this is minus. Then there is layer minus,
than
plus, minus, plus. Okay. So up to which, suppose up to this layer, there is a charge distribution like this. And after that, in this zone, there is equal number of positively ion charge and equal number of negatively ion charge. Okay. But from this position to this position, there is a distribution intentionally made because of the negatively charged layer. Okay. So this plane, this outside plane is called the diffuse layer. Diffuse layer, and this is the bulk solution. But in bulk solution, the concentration of positively charged particle and negatively charged particle is similar. But before that, there is a distribution of positive and negatively charged particles, and these are divided in 3 layers. The first one is the Stern layer, which is always fixed. The second layer is the shear plane, and the third layer is the diffuse layer. Okay, and now what is zeta potential in this layer, that is in the shear plane. In the shear, if we calculate the voltage, the shear plane voltage is called the zeta potential. Okay, the shear plane voltage is called the zeta potential of a particle. Okay, did you get it?
Okay. Thank you.
Yes. Yes. So here you will see, suppose at the layer, this is suppose Psi 0. It has highest voltage. Now, yes, it has highest voltage. Now, if we are going to the Stern layer, the voltage will be little bit reduced. Then, if you go to the shear plane, voltage will be much reduced. So this level, at this point, the value of the potential is we call the zeta potential. And if we go to the diffuse layer, the potential will again reduce, and in the bulk solution it will be neutral. That means there is no potential difference. The same charge, same amount of positive and negative particles are there. That is why it is called neutral. Okay, so if you look at the graph, you will see initially the potential is, this is potential versus distance curve. So initially the potential is high. There is a sharp jump of particle here, sharp jump of potential difference here, and after that, after it reaches the Stern layer, the potential will reduce like this, and this is the neutral point. Okay, neutral point, that means the solution reaches the bulk medium, and at this stage it is the shear plane and it is the zeta potential. Okay, so remember the zeta potential is the potential at the shear plane. Okay, if you go through the video or any other videos in the YouTube, we will much more clearly understand this. So we can see this. So
प्लीज द टाइमिंग 3 to 5 चेंज 2 to 4 हो सकता है मैम?
no, it is given from the NPTEL actually. So that is that the starting time is 3 p.m.
3 p.m. The time changes.
No problem. You join the class for 1 hour. I will upload the.
Okay, thank you. Please share.
Yes, I will upload the videos. You can check it from the YouTube also. So this video will be there in the YouTube. They will share. NPTEL will share with you the link of the video which we are doing today. So you will get all the update.
This video uploaded in the NPTEL login site?
Yes. We will upload. They will upload it in the. I will share the link and they will upload it. They will also share it with you or all the students, so they can share it. They can see it afterward.
Okay.
Okay, fine. So as the call will end in 5 minutes, I am creating a new link to continue. So now I can continue the rest of the lecture. So what I was showing the zeta potential video, right? So here you can see.
Stop using ChatGPT for your research. happens when a charged particle is immersed in a liquid such as an aqueous electrolyte solution. In this case, there's a positively charged particle surface, and somewhere there has to be a balancing negative charge. Typically, that will be in the form of ions absorbed onto the surface of the particle. And you can consider this to be a fixed or rigid layer of charged material. With an electrolyte solution, there's a uniform distribution of anions and cations in the bulk. Near the particle, anions, shown in yellow, will be attracted towards the particle, leading to a higher concentration of anions. And similarly, repulsion of cations, shown in blue, will result in a lower concentration of cations. This region is a diffuse layer of ions, balancing the charge on the particle. So we have a rigid layer associated with the particle surface and tightly bound material, and then a diffuse layer. And combined, we get the diffuse electrical double layer. There's a transition from the diffuse layer with an excess of counterions to the bulk solution with a uniform concentration of ions. Very close to the particle, material is either adsorbed or strongly associated with the particle, such that it remains with the particle when it moves relative to the liquid. The transition point between bound and free liquid is called the shear or slipping plane. But what does this say about the magnitude of the electrostatic repulsion between particles? If we have two such particles approaching, we know intuitively that there'll be electrostatic repulsion. But how is that quantified? And how does it look spatially
So just
as you
how
go?
I have said that there is a particle. I have shown in a different type that I have shown the particle is negatively charged, but here they are showing the opposite one. The positive charge particles are there in the particle layer. So obviously the negative charge particle will be attracted first, and they will create first the rigid layer, that is called the Stern layer, and there will be another layer which is the shear plane, where if we calculate the potential, that is called the zeta potential, which is a movable layer. And then comes the distribution of negatively charged particles and positively charged particles, which is diffuse region, and until when the charge becomes neutral, this diffuse layer is continued. And this is the bulk solution. And as there are two types of charge layer in this diffuse region, this is called the electrical double layer or EDL.
Away from the particle.
So now I have shown here the distribution of the potential. So it will be clearly shown in this
I'm going to
video that how
superimpose
the
on the
electric
schematic
potential
of the double
distance
layer
will change
the
along with the
graph
layer.
of electrical potential as a function of distance away from the particle surface. Electrical potential is something that's not usually described very well when explaining the double layer. But the concept's fairly straightforward. If you have a charged particle carrying, say, 100 elemental charges and a single elemental charge of the same sign infinitely far away, and you want to bring that unit charge up to where the particle is, then you have to provide energy. This is electrical potential energy and is expressed as a voltage. So the electrical potential is a measure of how much energy it takes to move a single point charge to the particle from infinitely far away. It's an indicator of the repulsion that's going to exist between particles as a function of their separation. So that's the connection between charge and potential. If we look at this diagram, then we have a starting potential at the surface, which is psi sub 0. The surface charge is
Yes. Now the psi 0 is the potential at this particle layer, which is the highest one, right?
screened
So now it is directly in a straight line, it is falling down because there is no positive charge in the Stern layer, right? In the stand layer, there is only negative charge, though that is why the potential sharply decrease, and that is why we are getting straight line here.
By the presence of adsorbed material of opposite charge. So the potential decreases between the particle surface and the slipping plane. The potential at the slipping plane is defined as the zeta potential.
So that is the slipping plane or shear plane that I have mentioned in the here. So that is the shear plane or slipping plane. Both are same. Okay, both are using interchangeably. Okay. So this is the potential drop from the particle layer to the slipping plane or shear plane, and potential at that point is called the zeta potential.
The potential continues to decrease beyond the slipping plane due to the electrolyte and polar nature of the liquid.
So now you can see that the potential will decrease further from the zeta potential until it will reach the neutral zone. And that is how the electropotential versus distance curve we are getting.
Distance over which it decreases depends on a number of factors. A thickness is defined as the distance at which the potential has decayed to 1 over E of its initial value. And this distance is written as 1 over kappa.
Okay, so this is the zeta potential. I have missed a previous question, which is what is the powder classification according to Richards and Brown?
Let's look at the effect of different electrolyte concentrations on the thickness. On the top left, we have a dilute electrolyte. The decay is slow.
So you can go and watch further what is the Debye length, how is it calculated and all. So the main zeta potential is explained in the previous video. And also there are other many videos in the YouTube available for the reference of understanding any kind of expression. You can search there. So what is powder classification according to Richards and Brown? Before that, we have learnt about the Gelder's particle. There are 4 kinds of Gelder's particle, that is group A, B, C and D. And in the Richards and Brown, there are 5 classifications, 5 class. So when the particle range is 0.1 to 1 micrometer, that is called the ultra fine powder. Next comes 1 to 10 micrometer. That is super fine powder. Next comes 10 to 100 micrometer, which is granular powder. Fourth one is the 0.1 to 3 millimeter. That is granular solid. And last one is the 3 to 110 millimeter. That is broken solid. So that is the classification of powders as per the Richards and Brown. Next comes the zeta potential. I have already explained the zeta potential. Next is what is the expression of electrophoretic mobility. So electrophoretic mobility is defined by mu E. This is V by capital V by L. This V, small v, is the speed of the particles speed of the charged particles. Then capital V is the voltage given in the zeta potential calculation, and L is the distance between two electrodes. Okay. This is the expression of the electrophoretic mobility. Next comes if the zeta potential is between -30 to -40, how the stability of the solution will behave. If the zeta potential is between -30 to -40, how the stability of the solution will behave. So we know that when the zeta potential value is high, then the particles will be repulsed from each other and they will be stable in the solution. Otherwise, if the zeta potential is very less, they will coagulate and settle down. So, -30 to -40 volt, millivolt or volt range gives moderate stability. Okay. Then, if it is 0 to ±5 millivolt, then the voltage, the potential value is very less, the potential value is very less, that is, they will coagulate. From ±10 to ±30, it will incipient instability. So -30 to ±30 to ±40 has said the moderate stability, and above this +40 to ±60, it is good stability, and ±60, more than ±60, it is excellent stability. Okay. Next comes, for monodispersed particles, multiple size peaks will be there. Is it true or false? For monodispersed particles, multiple size peaks will be there in size distribution. That is false, because if you see the size distribution curve, monodispersed particle means that has only one type of particle. So why it will have many peaks? It will have only one peak. Okay. If it is polydispersed particle, it will have as many as peak. And if it is grinded from some larger structure to the smaller particles, it will have different kind of peaks. Okay. So this is a size distribution curve, and it is false. So these are the questions I have discussed. So now I have some another question. So I have a question, you write. The size analysis of ground quartz particle is given. This is the size in millimeter and the mass fraction. Okay. This is the size of the screen. So different a stack of different kinds of different sizes of screens are there. So the first size is 4.76, then 3.36, then 2.38, 1.68, 1.19, and lastly less than 1.19, which is not mentioned. And here the mass fraction is 0, here 0.2, here it is 0.4, 0.3, 0.8, 0.08 and 0.02. Now calculate the cumulative mass fraction of particle of size less than 1.68 millimeter. Okay. So what will be its answer? So that means it is said that what is the mass fraction is left below 1.6. This is the 1.6 size pan. So you know, so that means less than 1.19 size means that is the pan, right? So less than 1.19 excuse me, 19 size sieve means this is nothing but the pan. So in pan we are getting 0.02 mass fraction of solids. Okay. Before that, in the 1.19 sieve we are getting 0.08 mass fraction of the solids, right? Above this is 1.68 where we are getting 0.3 mass fractions. So the question asks that what is the cumulative mass fraction of particle when less than 1.68? So if we go to calculate if we go to calculate the 2.381, in the 2.38 plane 0.4 mass fraction is there. That means when the mesh size is 2.38, (0.4% of mass 0.4% of the solid is retented here, and rest of the 0.3% of the solids are passing through it, and it reaches the, if it is 2.38, it reaches through here in the 1.68 zone, right? This is the 1.68 joule. It is reaching 0.3% is reaches there. Again, here through the mesh, the larger particles will be retained and the smaller particles will be flown away, will be thrown out, right? Not thrown out, it will be passed through the seeds. So it will reach to the 1.19 pen, and only 0.08% is going to the 1.19 pen. Again, it will be going, and the bottom one is the pen, and here only 0.02 is stored. So when we are asking in the question that what is the cumulative mass fraction of the particles less than 1.68 meter, that means we want to know that when we are sending the particles through the mesh of lesser size than 1.68, then what is the cumulative mass fraction. So we'll calculate here. It is 0.08 plus 0.02, and it is nothing but the 0.01. So this is the answer. If it is asked that calculate the cumulative mass fraction of particle size less than 2.3, so then at that time we have to calculate all the three. 0.3 plus 0.08 is 0.02. Okay, so as it is here asked as 1.68, so we are calculating as 0.1. Okay, this is how it works. Now time is almost up, but I have something to show regarding the mass mean diameter. So I will do a problem on surface mean diameter. Okay. So the question is calculate the volume surface mean diameter, that is nothing but the Sauter mean diameter of the following particulate matter material. So size ranges are given, and here the mass of the particles are given in gram. So it is given minus 704 plus 352. That means, why is it given minus? That means 352, 704, the size of particle is if the size of particle in between 352 micrometer to 704 micrometer, then only this mesh can retain the particle size. This is the, you can say, the undersize screen range. Like beyond 704, it also can calculate obviously, but below 352 it cannot retain, it will pass through. Okay, so above 352 to 704 this mesh can retain, and its mass is 25 gram. Similarly, in the next 352 plus 176, which is 37.5. Here it is 176 plus 88. A gram is 62.5. Next, minus 88 plus 44, it is 75 gram. And in the pan, only 50 gram of mass is given. In the question I have solved initially, that is the assignment question, there the mass of the particle is given and the diameter of the mesh is given, right? And we have to calculate only the mass fraction from the mass particle. But here nothing is given. We have to calculate the diameter as well as the mass fraction also, because you know the volume surface mean diameter is the summation of xi by di, I1 equals to n, right? So we will calculate here only. So this is the size, right? Now we are going to calculate the diameter, average diameter of the mesh. Average diameter of the mesh. And here we are calculating the fraction. So for the first, how it is calculated? It is just the average. 704 plus 352 divided by 2. How much is it? 704 plus 352 divided by 2. It is 528. Similarly, the range of particle, we are calculating the average diameter, right? So we are summing both the ultimate range and divided it by 2. So it is 352 plus 176. It is 264. Then 176 plus 88 divided by 2, it is 132. Similarly, it is, I am not writing explicitly again and again. Then 88 plus 44 divided by 2. This is 66. This is 66. And in the pan, it is given that, and in the pan, only the particle which has less than 44, diameter will be stored, right? So there is no another mesh beyond the pan. Pan is the last one. So this 44 will be the last one in the case of pan. Now all the diameter we got, right? Now the mass fraction. First we have to sum it up. How much is coming? 25 plus 37.5 plus 62.5 plus 75 plus 50. It is 250. Total mass is 250. And now we are dividing individually. So 25 by 250 equals to 0.1. 37.5 by 250 equals to 0.15. Similarly, third one is the 0.25. Then it is 0.3. And last one is 0.2. Now we have got all the diameters and the mass fractions, right? Here heading will be mass fraction, that is xi. Okay. Next, what will happen? We have to calculate it. So what is it? So first one is the 0.1 by 528, right? So 0.1 by 528 plus 0.15, 0.15 by 264 plus 0.25, 0.25 by 132 plus 0.3 by 66 plus 0.2 by 44. Now what will come? So we calculated individually. So it is 0.000189 plus 0.000568 plus 0.00189 plus 0.0454500, sorry, and last the 0.2 by 44, it is coming same, it is 0.004545. Now we're doing the summation. It is coming 1 by 0.0117414. So total it is coming 85.17 micrometer. So this is the mass mean diameter, volume mass mean diameter or Sauter mean diameter of the particle size. Okay. So here you can see that how we have calculated the diameter of the particles. So this is for today. I hope you have understood the problems what I have discussed from the beginning. You have understood the assignment problem, and you have also understood the rest of the questions, the MCQ I have done, and hopefully you will go through. And if you have any question, you can message or mail me. I hope you will find helpful this video afterwards. I will upload this video in the YouTube. So and the NPTEL will share with you the link of the video. So if you cannot join that live session, it is fine. You can also watch it from the video later, YouTube later. And till then, next class we'll meet on next Saturday. So till then, goodbye.